This video is all about 10.4, which is integrals and polar coordinates, and in particular, areas enclosed by polar curves. So very similar to our normal integration, our normal areas, but slight modifications. So let's kind of build up the theory a little bit. So to do that, let's first think about our normal curves and Cartesian coordinates or rectangular coordinates, whatever you want to call it. So let's consider a function y equals f of x, a function of x. Well, if we think about the most intuitive, the most kind of basic understanding of the integral, okay, let's let this curve be, positive. We could think of the integral as giving us the area beneath the curve, right? So if I integrate from point A to point B, that integral gives me the area beneath the curve. So that green shaded region. But let's kind of backtrack a little bit and talk about the process we built up to find this integral and how we kind of approximated the area before we developed the integral. Remember, the integral developed from these approximating rectangles, right? We had rectangles that we kind of broke our curve up into rectangles, and we found the area of each rectangle, and then we added those rectangles, and that gave us an approximation to the area, right? So what did that approximation look like? It was a sum, right? A finite sum. So we added like k number of terms together. Change my notation a bit here. Okay, so maybe I added together n rectangles, okay? And this stuff inside the sum, that's the area of my rectangles, right? Like the f of xi, that's like a point, let's see, we're kind of using left-hand points here. So these are my f of xi's, so these are the heights of my rectangles. And then this delta xi is these distances, which is the width of my rectangle. So I multiply these together. These terms multiply together give me the area of one rectangle. And then I add all those rectangles together and I get all these, the sum of these areas, right? That's how we built up that's how we approximated our area. And then we took the limit of everything, right? And it became an integral from a to b of f of x dx, right? So we took the limit as these distances went to 0. We made these distances thinner and thinner and thinner, these rectangles thinner, and that, as we took that limit, it gave us the integral. So we're gonna do a very similar process for areas in polar coordinates. All right. So let's think about this a little bit. We'd like to approximate this area. So first of all, what area am I talking about? Okay. When I have a polar curve, I want to find, let's say I want to find, how would a question like this be phrased? It would have like a curve r equals f of theta, and you'd be told to find area enclosed by the curve between two different angles, between, let's say, call it theta 1 and theta 2. Okay, so let's say theta 1 is this angle, okay, and then theta 2 is this angle. Okay, and this is my curve. Well, the area enclosed by that curve is the area in this kind of pi wedge between these two angles, okay, and it stops at the curve. Okay, so that's what we mean by these areas in polar coordinates, the areas enclosed by this curve. Okay, all right, so that's what we mean. But then the question is, how do we find this area? Okay, so let's start by trying to approximate it. Okay, let's try and approximate this area. How could I approximate this area? What shape could I break it into? Could I break it into rectangles? Well, I don't want to break it into rectangles, right? Because that would just be, if I first of all, it wouldn't be very easy. This doesn't break very nicely into rectangles, does it? It'd be kind of weird. You know, these rectangles are kind of sitting on this slope, and there's a lot of kind of dead space in there, so it wouldn't be a great approximation. So maybe these rectangles, these vertical rectangles, are not the way to go. What shape would be better? What shape would be better for my approximation? Circles, in particular sectors of circles, would work really well. So what I'm going to do is, let's say I want to find the area in between these two angles here. I'm going to break this into sectors of a circle, meaning I'm going to kind of like take a slice here, okay? And then I'm going to pretend like this curve isn't sloped here, like that it's just kind of a circle. It's got the slope of a nice circle, okay? So there's not much variation here. It's just on the outside, it's just a circle with this radius, okay? If that's the case, I can find the area of that sector really easily. Okay. So before we go too much further, let's think about the area of sectors of circles. First of all, if I have a full circle, that area is what? You know, it's pi r squared, right? Where r is the radius. Okay. Okay. But this is the area for a full circle, and I'd like some way to modify this to get I can plug in different angles and get areas of different sectors of circles. Okay. So this is for a full circle. All right. Let's rewrite this as 2 pi r squared over 2. Same thing, right? And now this, it might not be obvious, but this kind of tells me, this is kind of the formula I'm looking for, okay? 2 pi is the angle of the full circle, right? Like if I have a circle and I do an angle of 2 pi, that's like the entire circle, okay? If I plug some other angle in here, that's going to give me the area of that sector. So for example, if I plugged in pi over 2 here, okay, that's going to give me the area of that piece right there. And if I plugged in, let's see, 0.44 pi, okay, radians, which would be something like here, it would give me the area of that angle. So what we have here is really what we have is a formula for the area of the sector of a circle, where this is our angle measured from this line here, okay? And we can make this a bit more general, okay? What if we want the area of a sector of our circle, but we don't want to start measuring the angle right here at this axis? What if we want, you know, the area of this sector? So I'm not starting at that axis there, I'm starting at this line here, okay? Really all we care about is the width of this section, okay? So really the area of that sector of a circle would be like theta 2 minus theta 1, okay, r squared over 2. Okay. All right, so now let's go back to our page and see how this relates to our integral. Okay, I'm going to break down my section into kind of like pie slices. All right, so maybe I want to find this area. I'm going to break it into sectors of a circle. I can start by, let's say, you know, I'm trying to find this area. I can start by breaking it into 2. Okay, so let's look at this green area first. Okay, I'm just gonna pretend that instead of this kind of bumpy curve, I have a nice circle on the edge. Okay. Okay. So what would the area of this sector of a circle be? Well, it'd be whatever angle this is. You know, theta. Let's call this angle theta 1 here. Call this angle theta 2. Okay. Well, then that angle in total is going to be theta 2 minus theta 1. Okay. And you know, they're in terms of pi, right? Okay. So actually, I don't need that pi on the bottom there. Okay. Usually there's pi's, right? So it's like 3 pi over 2. You know, those pi's aren't really necessary. Okay. That's just a notation I put in. So really what we have is theta 2 minus theta 1, width of this angle. Okay. Then divided by 2, and then times r squared, which is our radius, which is what? This distance here. Okay. But this is a polar equation, right? Okay. So what is r? We have r is f of theta, right? So r is some function of theta. So I can replace this r with f theta, which I'm going to do here. And then what's this theta 2 minus theta 1? I could think of that as delta theta, my change in theta. So really, if I take all that into consideration, I could write the area of this green section as 1/2 f theta squared delta theta. So that's the area of that one green piece. Now, if I'm gonna split this up into a couple sections, well, I would find the area of this green piece, then I'd find the area of this piece and add them together. And as you might expect, the skinnier I make these pieces, the better my approximation is. Okay. So let's say instead of having 2 pieces, okay, let's say instead I broke this up into several pieces. Okay. So one of my pieces was here, another was there, another was here, here, and I add all these together, and I should get a real good approximation to my total area, right? Okay, so that's how the approximation works. And as I take the limit of those, making those slices thinner and thinner and thinner, meaning the difference, how do I make them thinner? I'm taking this delta theta to be smaller and smaller and smaller. Okay. What happens? I should end up with an integral, just like I did with Cartesian coordinates. So as I take the limit of that delta theta to be smaller and smaller and smaller, what's going to happen? Well, my summation is going to turn into an integral sign, and I'm going to be integrating from, you know, whatever this angle is, theta 1 to theta 2. So instead of a and b, I could write like, I'll call them theta a and theta b. How about that? And then what's gonna happen in the 1/2? That's a constant, so nothing happens to it. F theta I is going to become just f theta. So the f theta I is here. They were like, I picked one particular point and made that the radius, right, for each piece. Okay. But as I take the limit of those, making those angles closer and closer and closer, I'm just considering all my f thetas. It's squared. Okay. And then what happens to my delta theta? That becomes d theta. So if you can follow all that, great. If not, this is the formula we need. Okay. So if I want to find the area of a polar curve, let's say this is my polar curve. I want to find the area between angle theta A and theta B. That area is going to be theta A to theta B. Well, the area is given by this. Okay. This integral. Integral from theta A to theta B of 1/2 f theta squared d theta. Okay. So let's see this in action. Let's do an example real quick. Let's find the area enclosed by the curve r equals e to the power of theta between the angles theta equals 0 and theta equals pi. So first of all, what does this curve look like? Okay, so at angle 0, our radius is 1, and then as our angle grows, our radius should grow. So our curve should look something that's kind of like one of these outward spiral things. Okay. So I want to find the angle, I want to find the area enclosed by the curve between angle 0, which is just here, okay, and angle pi, which is here. Oops. Where'd I go? Okay. Okay. So the shaded area I'm looking for is this shaded area, right? But it's not a circle, it's getting wider, right? So I kind of drew this poorly. Let me take another stab at it. So our curve kind of looks like this, and it keeps spiraling outward. Okay, so this is not a circle here, it's getting wider and wider and wider. So there's no nice formula for it, I just have to integrate it. Okay. So how do I integrate it? Well, let's see, I set up my integral. Where's my theta A, theta B, okay, 0 and pi. So I integrate from 0 to pi. I got my 1/2. What's my f theta? All right, I got r equals e to the theta. So that e to the power theta is my f of theta. And then I integrate in terms of theta. Okay. And now it's just integration. So I integrate this thing. Let's see, I can pull the constant outside. E to the power of theta squared, that's the same thing as e to the 2 theta, right? So I integrate this. And I get this thing from pi to 0. I evaluate and I get see, e to the 2 pi over 4 minus 1/4. Okay. And that's my area of this shaded region. All right, pretty straightforward. What can help a lot is symmetry. Okay, so this can save us a lot of time. So what do I mean by symmetry? Right. So this is, this integration stuff is the only thing this section's about. We're not going to do arc length. There's arc length in the book in section 10.4. We're not going to do arc length. We're just concerned about areas. So really, we've learned everything we need to know for 10.4. The rest is just tricks, important tricks, but just tricks. So let's say I want to find the area enclosed by this curve for theta between 0 and 2 pi. Okay, that means I want to find this entire shaded area. All right, how can I find that area? Well, notice that this thing is symmetrical around this vertical axis here. Okay, so the area on this side is the same as the area on this side. So I don't need to integrate the whole thing. I could just integrate this left side. I could just find the area of that left side and multiply it by 2, and then I'd have my total area, right? I could just find this, multiply by 2, and that'd give me the total area. Okay, so this is a way that symmetry can make our life easier. This only works because these sides are mirror images of each other. Okay, so that wouldn't have worked in this case, because there's no symmetry here, but it does work in this case because our curve's nice and symmetrical. So how do we take advantage of this symmetry? Okay, well, I want to find this area. Okay, so what is this area? Well, it looks like it starts at angle negative pi over 2 and goes to pi over 2. Okay. All right. So think about this. If I'm at angle 0, right? kind of right on top of this axis. And then if I come down to negative pi over 2, that'd be like here, okay? So if I integrate from negative pi over 2 to 0, that's like integrating in like this section, this quadrant. And then if I integrate from 0 to pi over 2, that takes me to, that lets me integrate over this quadrant 1. Okay. And there's the polar curves kind of get confusing because there's a couple of ways to do this. We could also integrate this curve from what, 3 pi over 2 to 5 pi over 2. And that should give us the same region, okay, as integrating negative pi over 2 to pi over 2. So kind of weird. When you're finding these areas, this is something I'll go over more in the problem video, you just have to look at these graphs. You know, it really helps to draw these graphs to get an idea of what's going on. You draw the graph and you say, okay, if I want to find the area of this region, what angles capture that region? I look at this and I say, well, I want this quadrant here, so I want to start integrating. I want to integrate from here to here. Okay, what angles are those? And I would look at this and say, well, negative pi over 2 to 0, and then 0 to pi over 2. Okay. Let's continue. So to find the area of that shaded region, we should do, let's see, negative pi over 2 to pi over 2. And then what do? I got my 1/2. What's my f theta? 1 plus sine theta. I need to square it and integrate in terms of theta. So the rest is integrating. So I'll pull out my 1/2. And then really I should be multiplying this by 2 to find the total area, right? So I got a 2 out here. When I bring the 1/2 out, the 2 and the 1/2 cancel. Okay. And then I'm left with the integral from negative pi over 2 to pi over 2 of 1 plus 2 sine theta plus sine squared theta d theta. This integral. And the rest is just integrating. I integrate, let's see, I need to change this sine squared to, I need to use my double angle identity, right? Okay, so change my integral to this. Now I integrate. Double check me on this step. So check, try integrating from here and see if you get the same thing. And we should evaluate that from pi over 2 to negative pi over 2. Plug in our values, and what do we get? Let's see. We can simplify this a bit further. Okay, getting that. Evaluating, let's see, 3 pi over 2 over pi over 2, or excuse me, 3 pi over 2 over 2. Okay, that's what, 3 pi over 4 minus 0, because cosine of pi over 2 is 0, minus 0, because sine 2 pi over 2 is sine of pi. Okay, so I got 3 pi over 4 minus, okay, let's plug in negative pi over 2 the same thing. So my total area should be what? 6 pi over 4, which is equal to 3 pi over 2. So that should be my total area, okay, for this curve here between 0 and 2 pi. Right? So that symmetry helped us. Maybe it didn't save us a whole lot of work in this one, but I wanted to show you the symmetry because this symmetry is going to be very helpful on your WebAssign homework. Okay. And it's going to be especially helpful when we start thinking about areas between curves, which is our next topic. So this is very similar to the material we covered in section 6.1. Okay, so remember when we had y equals f of x and y equals g of x. Okay, so let's say this is f of x and this is g of x. Okay, and I wanted to find this shaded region, the area between those curves. Remember how we did that? It was the integral, from a to b of the top curve minus the bottom curve. What about if I have r equals f of theta and r equals g of theta? What if I have two polar curves? How do I find the area between those polar curves? Well, the principle is the same, okay? It's the integral of it's the area of the outer curve minus the area of the inner curve, okay? So we need to use our same formula here in this integral. So it should be like 1/2 f theta squared minus 1/2 g theta squared d theta. Okay, but the principle is the same. It's like I find the area of the outer curve and I subtract away the area of the inner curve. Okay, so nothing too radical here. Let's try finding the area inside these two curves. R equals 4 sine theta, and outside the curve r equals 2. Okay, so we have the way this question is phrased might throw you at first. It's the area inside this curve, r equals 4 sine theta, and outside the curve, r equals 2. Okay. So if you're ever in doubt, graph these. Graphing them by hand is great practice. You're going to have to maybe do that on a test, something like that. Or you could use like Desmos or something if you're in a pinch, in a hurry. So let's see, I graph r equals 4 sine theta. It doesn't have to be a perfect graph. I know, just from experience, this is going to be a circle. I don't really memorize it. I just kind of reconstruct it from memory, or not memory, but kind of reconstruct it. I go through the steps. So let's see, at angle 0, my circle is going to be at radius 0. Okay, and so it starts here, and then as the angle gets bigger, my radius gets bigger, and so at pi over 2, it's up here at 4. Okay, and then it loops back down. So it's this is supposed to be a circle. It's a circle like this, okay, that goes up to 4. And it's completely above this horizontal axis. All right, and then what about the circle r equals, or excuse me, what about the curve r equals 2? Well, that's just a circle with radius 2 centered at the origin. So that looks like this. Okay, so these are my two curves. Now let's look at what they're asking for. They want the area inside this curve, okay? So area inside this curve would be like all that, right? But then we want outside r equals 2. So we don't want this stuff here. So the area we're looking for is just that shaded region, okay? So how do I find that? First of all, I haven't drawn it very well, but this is, let's see, I'll try and draw it again. Usually it helps to draw it small for me. So I'm looking for this region, and again, my drawing is not great, but this is symmetrical. Okay, so this right side is the same as this left side. Okay, and usually you can tell by looking at it where the symmetries are. So let's just try and find this right piece. Okay, so how do I find the area of this right piece? Well, again, it's going to be outer curve minus inner curve. So let's zoom in on that right piece a bit. essentially what I have is, okay, I have these two curves. I'm looking for this area. What would be my outer curve? What would be my inner curve? Well, this would be my outer curve, and then really my inner curve is this piece here. So first of all, what would my area look like? I know it's going to be outer minus inner, right? So it's going to be 1/2 4 sine theta squared minus 1/2 2 squared. Okay. So I know my integral looks like this. So this, the integrand, the stuff I'm actually integrating, that's not too hard to find. It's just outer minus inner. What can be hard, what can be difficult, is finding the bounds where I integrate this. Okay. What are my bounds here? What are my a and b? And let's go to a new page and let's draw this one more time. I feel like I gotta draw it somewhat big to make a good point. So let me draw this and pause it. Okay, I've drawn somewhat better. So I'm trying to integrate this region, okay? And I know it's outer curve minus inner curve. I know the form of my integral is 1/2 4 sine theta squared minus 1/2 2 squared. The problem is, where do I start integrating? Okay, where do I start integrating this region? Where does this, at what angle does this region begin? It begins at this angle, whatever this angle is, and it ends where? It just ends on this axis, right? So it ends at pi over 2. Okay. And I'll kind of run out of space there. Okay, it looks like it ends at pi over 2. What I'll say is that you should plug the angle pi over 2 into your equations and make sure you end up at this point or on this line for both of them. Okay, because polar curves can be tricky like that, where we can have a polar curve like this, okay, and maybe we need to find this point, but maybe our equation is like r equals -2, right? In that case, this point corresponds to the angle this point corresponds to the angle 3 pi over 2, which is down here. Okay. So it can be a bit confusing. Usually you'll just be able to look at it and get the right angle, but I'll say be careful. That's my little disclaimer. Okay, so this angle here, this angle where we end our integration is pi over 2. What's this angle here? Well, notice it's going to be the angle where these curves intersect. Okay, so how do I find that? I'm going to set one curve equal to each other, or one curve equal to another. So I have 4 sine theta is one curve, and then the other curve is 2, right? Now I'm going to solve for theta. So sine theta equals 1/2. So what angle gives me a sine value of 1/2? Well, that would be pi over 6. Okay. So that's the angle where my curves intersect. So that's where I should begin my integration. All right. So now let's go back to our original page. I have my integral. I now know my angles, pi over 6 to pi over 2, and the rest is just integrating. And that's going to give me my area. And I'll leave this integration step to you guys. Let's see, when we square this, we're going to end up with a sine squared, so we're going to need to use the double angle identity. And then this is just going to give us a constant here. So pretty straightforward integration. another way we might see the questions phrased is the area inside both curves. Okay. So let's draw this. What does 3 sine theta look like? That's another circle like this, kind of sitting on top of the axis. Okay. What does 3 cosine theta look like? That's another circle kind of to the right of our vertical axis. So our curve looks like this, and we're trying to find the area inside both curves, which is kind of this overlap here. Okay. So what is that area? This one is another interesting thing. We can use symmetry here, and we need to find some intersections of curves and all that. So let me again draw this a bit bigger so you guys can get a better picture. Okay, so our curves look like this. And I'm trying to find this area, the area inside both curves. Well, first of all, let's think about this line where these curves intersect. All right, let's actually draw it in about blue. So let's think about this line here, this angle. Okay, the curves intersect at this point here. Now, this kind of divides our region in half, right? So let's consider this lower shaded blue region. What is the area of that region? Well, actually, excuse me, that region has nothing to do with this curve, this circle, right? This is just the area of, let's do it in yellow. This is just the area of this circle from this angle 0 to whatever this angle is. Okay, so that shaded blue region is really just the integral from some angle to some, let's say angle 0 to whatever this angle is. We'll call it theta b for now. It's the integral from 0 to theta b of just this curve here, which is, that area would be this. And then if I multiply this by 2, that should give me the total shaded region, right? Okay. So I'm multiplying it by 2 here. All right. Now, the only thing missing is this angle. What angle is that? Again, I'm going to set one curve equal to each other, or the curves equal to each other. So I set 3 sine theta equal to 3 cosine theta. And then I solve for theta. Well, I can divide 3 from both sides. And then I ask myself, okay, where does sine theta equal cosine theta? A couple places, right? Pi over 2, pi over 4, 5 pi over 4. But which angle is this? That looks like 5 pi over 4. Or excuse me, it looks like pi over 4. So I should integrate from 0 to pi over 4. And then that's going to give me, just the integral is giving me this blue shaded region, and then I multiply by 2 to get the total shaded region. Okay. So another powerful application of symmetry. This one would be very hard to solve without that symmetry. So symmetry is important. Okay. And really, that's all for this section. It's not necessarily easy or anything. You know, these trig integrals are hard, but there's not a lot of material here. It's just really the formula and then some tricks. Okay, so that's the material, and then hopefully the problem video I make will give you more insight into how to use these tricks of symmetry and things like that.